Hey everyone, and welcome to this explainer. Today, we are tackling a massive fundamental engineering challenge. We're looking at how power actually moves through the complex machines we rely on every single day. We're talking about energy transduction in multi-domain machines. It's this highly practical science of how energy constantly shifts its form to get real, physical work done in our world. Let's get right into it.
To really wrap our heads around this, I want you to picture a heavy crane on a construction site, or, even just a simple elevator in a building. Here's our central mystery. How exactly does an invisible current of electricity, just flowing silently through a wire, manage to physically lift a massive heavy weight? It's a pretty profound question when you stop and actually think about it. We're literally talking about getting energy to cross a physical boundary. It has to leap completely out of the electrical domain and over into the mechanical domain. So, how on earth does it make that leap?
Okay, let's dive into this. The answer to our mystery boils down to energy transduction. That's the fundamental principle of moving power across completely different physical domains. It's absolutely crucial because it's the core framework that helps us engineers understand, map out, and predict the mechanical behavior of highly sophisticated hardware. Without it, well, that electrical energy is just trapped in its wire forever. It desperately needs a bridge to interact with the physical world.
Which brings us to Section 1, Meet the Shapeshifters.
So who actually builds this bridge between the domains? Well, I like to call them the shapeshifters of the engineering world. In technical terms, we're talking about two-port transducers. They're these hidden components that facilitate the movement of power right through complex mechanical systems. Engineers use these two-port models to accurately calculate exactly how energy shifts from an electrical input directly into a mechanical output, making absolutely sure nothing gets lost in translation. Now, what's really interesting about this is that these two-port transducers basically come in two very distinct flavors. On one side, we have transformers, labeled TF. They're kind of the steady players. They maintain consistent variable types during a transfer. Think of simple levers or gears, right? They take mechanical motion and just pass it along as mechanical motion. But on the other side, we have the gyrators, labeled GY. These are the wild cards. They uniquely convert effort into flow and vice versa. An electric motor is a perfect example of this. It takes electrical voltage and current and completely flips it into mechanical speed and torque, a total game changer.
Moving right along, let's hit Section 2, the energy flowchart. Let's move to and see how this builds, because how do these components actually collaborate to solve our initial mystery of lifting a heavy weight? It's essentially this beautiful relay race of energy moving through our machine. Step 1. Raw electricity enters the gyrator. That's our electric motor, turning that electrical input into rotational power. Step 2. This newfound mechanical energy gets handed off to the transformers, our gears, which step in to adjust the physical force. And finally, Step 3. This perfectly tuned mechanical energy is applied to actually lift our physical weight, which is an inertial load represented by the letter I.
It's just such a powerful realization, isn't it? We can take an incredibly complex piece of multi-domain hardware. I'm talking about something with thousands of wires, complex circuits, and heavy-moving metal parts, and we can simplify its entire existence down into just a few connected boxes. This simple sequence of energy changes strips away all the noise. It just reveals the beautiful, underlying structural language of how hardware actually works.
All right, let's wrap things up with Section 3, Mastering Multi-Domain Mechanics.
Now that we've seen the micro view step by step, let's zoom back out for a second. Why does this all matter? So the crucial point is, by using this framework, you gain the absolute power to model complex multi-domain machines using two-port transducers. You learn to visualize functional flowcharts instead of just getting completely lost in the mechanical weeds. And that ultimately leads to a deep, highly predictive understanding of mechanical behavior. You stop seeing just a confusing, messy machine, and you start seeing the logical, elegant flow of energy.
Which leaves us with one final, pretty exciting thought. Our world is absolutely full of these multi-domain machines, bridging physical boundaries every single second of the day. From the alternator tucked inside your car to that tiny little vibration motor inside your smartphone, energy transduction is literally happening everywhere. So how will you use this framework to visualize the hidden energy changes in the hardware all around you? The next time you press a button and something physical moves, try to mentally map out the shapeshifters making it happen. Thanks for joining me on this explainer, and keep looking for those hidden mechanics in your world.